We are in week 6, if you can believe it. So the cat's excited about that. We're over a third of the way in to the course, looking at functions of several variables. And as I mentioned last week, we're going to be jumping ahead here a little bit in the book to talk about tangent planes and the concept of differentiability. So we're kind of jumping ahead. For reasons that'll become clear. There's a lot of good things about this book, but one of the things the book does is it kind of shortchanges you on what it means to be differentiable, and it doesn't really tie it into the theory of what comes later. There's a lot of theory that's based on what it means to be differentiable, so I want to do that first because it's a natural time to do it. We've already talked about partial derivatives. And partial derivatives, remember, are slopes in a particular direction. So we'll just go ahead and most of the week we're going to be spending here on section 15.6, making sure we understand where these things are coming from and what they mean. So let's go back to Calc 1. In many ways, easier, more simple times. Because in Calc 1, we had y as a function of x. We had a single independent variable, and we had our dependent variable. And we had the concept of the derivative. And the derivative, remember, was the limit of f of a plus h minus f of a all over h. And we can think of what was happening here geometrically on the graph of y equals f of x. We've got our function here. We've got our particular point A we're looking at. And if we move over to some value a plus h, the difference quotient here is the slope of the secant line. And as h went to 0, this would produce the slope of the tangent line, provided that limit existed. Right? And so in Calc 1, we had the following. If f prime of a exists, so as long as this slope existed, the limit of the slope existed, then f is locally linear at the point a comma f of a. And what that meant is that you could approximate the function by the tangent line. So this line here, that was your so-called tangent line. And so this was the concept of locally linear. And so for locally linear to happen, all you needed was for this limit to exist. Right? And what we're going to see in Calc 3 is that we can have partial derivatives existing just fine, but the function not be locally linear. So let's talk about how we would generalize the concept of tangent line into what we're doing. So let's generalize the scenario. We got our y equals f of x. We've got our tangent line at a comma f of a. Y equals f of a plus f prime of a times x minus a. And let's just look at this from a rate of change approximation point of view. All right. So here's how I like to think about what's happening with this tangent line. And we've all been through the Calc 2 stuff with infinite series and all that good stuff. But here's how I like to think of it. F of a, we're sort of looking at the curve. We're looking at the function near x equals a. So f of a is what you actually start with when x equals a. And then I like to think of this as sort of a first order correction term. So it's a first order approximation in the following sense. Okay, I'm looking at here the change in the inputs, which in this case are x's, and I'm multiplying it by the rate of change of outputs to inputs. Okay, so if x, if my input x, went off the screen there, x is close to a, then the f of x would be, well, it'd be close to f of a, and if I want to get a little more specific as to how close to f of a is, I would add this correction term. Right? That's the whole idea of locally linear. Right? And so if you think back to your Taylor series, Maclaurin series, I don't know what kind of stories you had in those, except for Adam, because Adam had me in Calc 2. But this is kind of like the idea. Like we've got this initial value, and then we're going to add this first order correction, and that's how we're going to do it. Okay? So with this in mind, we can guess a formula for a generalized concept in Calc 3. Because in Calc 3, instead of having one independent variable, we'll start off with two independent variables. So in Calc 3, we'll look at z as a function of x and y. And so then we'll be graphing stuff in 3 space. Here's our x, y, z. And so we'd have some surface here. And we're going to look at a particular point in the domain a comma b. So how can we generalize this? Well, the dependent variable wouldn't be y, it would be z, equals, and let's say if we can, see if we can generalize this notion here. So the first part is going to be the function value at the point. So the function value at the point would be the function value at the point a comma b. Then we add on this first order correction. Now back in Calc 1, we only had one independent variable, x. So we looked at the rate of change of outputs with respect to inputs. That was the derivative with respect to x, times the change in inputs. That was the change in x. Here we have how many independent variables? We not only have an x, we also have a what? A y. So we can have two of these first order correction terms. So we'll have one of these terms will be a first order correction in the variable x, and then we'll have a second order, or a second first order correction with the variable y. Okay? So what did we do? We looked at the rate of change of outputs with respect to inputs. That was the derivative here, but the derivative was the rate of change of the outputs with respect to the inputs being just x. So here, I can still do that, right? But the derivative is going to be the derivative with respect to x at that point, times x minus a. So this is trying to capture the change in the function as a result of changing the x, and then what would go here? What would help me estimate the change in the function as a result of changing the y? Yep. We would have the partial derivative with respect to y times the change in y. So the first thing, do you see how this is generalizing what we did here in Calc 1? We have our initial function value, and then we're trying to figure out, if we move off of that point, what the approximate change in the function will be. In Calc 1, we have only one independent variable, so we look at that rate of change times the change in the independent variable. In Calc 3, we've got 2, so we're going to move off in the x direction, see what that is, and in the y direction. Now, over in Calc 1, this object, if I graphed it, this is... There's a lot of busy traffic today. This is a number here. This is a number here. This is a number here. The only variable we have is x to the first power, and so that gives us a line. All right, so that reinforces the fact that we have a line happening here. Looking over here in Calc 3 now, this is a number. 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 So if I look at the variables, I've got z, x, and y all to the first power. And what kind of object is that going to produce? Nope, not a line, because we've got z, x, and y all to the first power. That's a plane. Yep, that's a plane. So, very good. All right, so this is where we would say, okay, well, this is how we could define a tangent plane. Whoa, what is going on there? Yeah, so tangent plane. I don't know why it keeps grabbing that. You just define the tangent plane this way. Okay. So that's one way to get to it, is just sort of looking at what goes on in Calc 1, thinking about rates of change and generalizing it. But there's another way to look at it geometrically. So let's say you are on this surface here, z equals f of x, y, and you were looking at this point, a comma b comma f of a, b, and you wanted to find a plane that was tangent to the surface. So if I think back to the recipe for a plane, so in order to get a recipe for a plane, I need a point, x naught, y naught, z naught, and I need what kind of vector? So remember back to when we built planes? We had a point and a what? Normal vector. And so if we had the normal vector, say a, b, c, then we get the equation of the plane a times x minus x naught plus b times y minus y naught plus c times z minus z naught all equal to 0. Don't forget the equal to 0 part. Okay? And this comes from the, once again, this came from the dot product. So, this was towards the end of chapter, well, not towards the end. Yeah, towards the end of chapter 13, we talked about how to build planes from points and normal vectors. So if we wanted to do that here, okay, then we need to come up with a normal vector. Because right now we got a point. What we'd try to figure out then is what's the normal vector. Okay? And how does that relate to partial derivatives? So let's take a look at what we talked about last week when it comes to partial derivatives. If we looked at fx at a, b, remember that's the derivative with respect to x treating y as a constant. So what we could think of is we could think of fixing y in this case as b and slicing the surface. So this would be the line where y equals b. And then fx at AB would be this slope. The slope here would be fx at AB. And likewise, if you look at fy of AB, that's the derivative of f with respect to y holding x as a constant. So we can think of slicing this. If I fix x equals a, then the slope here would be fy at AB. I'm going to move this over here now. Just get it out of the way. So that's the name of the surface here. Oops, f of xy, I should say. Okay? So you hold y constant. In this particular case, y equals b. You slice the surface, you get the curve. You take the derivative with respect to x and plug a into it. That's going to give us the slope there, the zx slope. And then do the analogous thing, holding x equals a, taking the derivative. That's going to give us the zy slope. All right. So from these slopes, I can get two vectors that live in the plane. So if I kind of zoom in on this and what I want, once again, I'm going to try my best to keep the colors consistent here. So there's that, and there's that. We're trying to get this normal vector. From these two things, I can get two vectors. I can get two directions of the tangent line. You follow? So what would be for the blue here, we're holding y constant. The slope here in the xz direction is fx. So for the blue vector, I'll call this v. So the blue vector, we're holding y as a constant, and we're changing the x. So if I move one unit in the x direction, I'm not going to moving any units in the y direction because we're holding y constant on this line. And then how far will I move in the z direction? Well, this is the rate of change. So that would be fx at AB times 1 unit in the x, and that would be the z. So this would be your change in x, change in y, change in z. And we'll call this vector w. The vector w is going to be the vector here for this tangent line. It's the tangent line that we get when we hold x as a constant. So once again, going through delta x, delta y, delta z, delta x will be 0. If we pick delta y to be 1, then delta z would be fy at AB times 1. Are there any questions on how we get these vectors here, v and w? We're going back to the basic principles of vectors here. Vectors are components. We look at the change in x, change in y, change in z. So we're assuming a unit change in delta x and delta y, and then using the partial derivative to give us what that change in z would be. Okay. Now, how would I get the vector n from the vectors v and w? This is something we talked about. So what can I do to get the vector n in terms of v and w? Yep, the old cross product. Very good. So this would be v cross w. All right. So let's go ahead and work that out. So n would be the cross product. So we're going to get the cross product set up, the I hat, j hat, k hat. And then for v, it's 1, 0, fx. And then for w, it's 0, 1, fy. And let's see what we get. We get I hat times, I ignore the row and column, the I hat is in. I've got a 0 minus fx. Then I get a minus j. Wipe out the row and column, that's in. I get a fy minus 0 fx, so fy ab, plus my k hat, wipe out the row and column, k is in. I've got 1 minus 0, which is 1. And so I get my n hat to be minus fx at ab minus fy at ab, positive 1. Any questions on calculating that cross product? All right, so here's our normal vector then. So going back to definition of plane, which I did, wait, I put that here, didn't I? There it is. So definition of plane, here we go. So the point that we've got on the surface is a, b, f of a, b. The normal vector we got is minus fx at ab minus fy at ab, 1. So if I go through and use the recipe we learned a few weeks ago to get to our tangent plane, we've got the x component times x minus a, the y component times y minus b, the z component times z minus f of ab. So we would get to here. All equal to 0. And so then if we solve for z, we would add over the f of ab. We'd add over the fx piece. And we'd add over the fy piece. And so there is a geometric motivation as to why we would want this to be the tangent plane. Okay? And one of the big themes in calculus, hopefully even going back to pre-calculus, is understanding the connection between the algebra and the geometry. So it's one thing to just sort of guess the formula in terms of rates of change, and now we've got this perspective which kind of comes at it geometrically. Hopefully you'll spend some time this week looking at both of these things and seeing how they connect. All right. There's nothing I hate more if I just, here's the formula for the thing. Memorize it, put it on a flashcard, right? I always like to try to motivate and explain where these things come from. And especially at the Calc 3 level, you may not have been able to come in up on this on your own. However, you should be able to kind of see how it's fitting together. Okay, so here's all of this put together here. So let's do some examples. Write the equation of the tangent plane at the indicated point. Graph the function along with the tangent plane near the point of tangency. What do you notice? Now I've got some exciting news about graphing that I learned over the weekend. We'll talk about that. Okay, so tangent plane. We've got this formula. Z equals f at AB plus fx at AB times x minus a plus fy at AB times y minus b. So this is our tangent plane formula. Hopefully you understand. If you remember the tangent line formula from Calc 1, hopefully this is just, once again, you don't have to memorize it per se. You just kind of know what it's going to be, right? If you understand the concepts here. So in our particular case, the particular point we're looking at, AB, is the point -1, 1. So here's how I recommend proceed through this problem. Because a lot of times what will happen is you'll get some expression z equals something. And remember, at the end of the day, this expression should look like z equals a number plus another number times x plus another number times y. The only powers of variables that should be here are first powers. And oftentimes, students will forget to substitute things in, and they won't have tangent planes. They'll have these weird surface type things. So this is how I recommend we proceed here. We start off with our fxy, x cubed, or x squared rather, minus 3xy plus y cubed. And then we're going to go ahead and calculate our fx and our fy. So this is what we talked about at the end of last week. What's fx? Fx, the derivative of the function with respect to x, holding y as a constant. What's fx going to be in this particular case? Whoops. So we're going to get, there you go. So the derivative of x squared with respect to x is correct. That's 2x. Good. Minus the derivative of 3xy with respect to x is going to be just 3y, because we're taking the derivative with respect to x. The 3 and the y are both constants. So the 3 and the y will stick around. Derivative of x is 1. And then what's going to happen to this y cubed? If we're treating y as a constant, like 2, what would the derivative of 2 cubed be? 0, because it's a constant. So that would be the correct derivative there. Okay. What about fy then? Now I switch it around. Now x is the constant. What's the derivative with respect to y? So if y is a constant, what's the derivative of x squared going to be? Yeah, so x squared would go to 0. The 3xy would be minus 3x, and the y cubed would be 3y squared. So let's just take a moment and make sure everybody's cool with the partials with respect to y. So x squared is gone. The derivative of 3xy, you treat the x and the 3 as both constants. All right. So now what we're going to do is we're interested in the point negative 1, 1. Okay, negative 1, 1. So now we're just going to plug negative 1, 1 into each of these. F of negative 1, 1. Fx at negative 1, 1. Fy at negative 1, 1. So just take an extra step and plug these in now before we start plugging things into that formula, because otherwise you'll there's a lot of room for mistake there. So plug, once again, these are your x's and y's, so xy. So what do you get when you plug in negative 1, 1 to f of xy? So what's the f of negative 1, 1? So negative 1 squared is positive 1. Negative 1 times 1 is negative 1 times negative 3 is positive 3 plus 1 cubed, 5. All right, let's plug this into fx. Negative 1, 1 into fx. What do we get? Negative 5. And last but not least, plug negative 1, 1 into Fy. What do we get? Six. Very good. All right, now we're going to put this into our formula. So z equals f of negative 1, 1 plus fx at negative 1, 1 times x minus the x coordinate, negative 1, plus fy at negative 1, 1 times y minus the y coordinate. And now we just go in and feed in these numbers, 5, negative 5, and 6. Z equals 5 plus negative 5 x plus 1 plus 6 times y minus 1. So 5 minus 5x minus 5 plus 6y minus 6. So we get z is minus 5x plus 6y minus 6. Any questions on the simplification there? All right, so the exciting news I have to share is if you were with me through the calc sequence, calc 1 and calc 2, you know that I really love Desmos. I kind of favor Desmos over GeoGebra. And turns out Desmos now has a 3D beta working. So let's fire up Desmos here and check our answer on Desmos to see if Desmos can show us what we need to see. So if you go to desmos.com, you'll see up here introducing Desmos 3D. There it is. Let's just go ahead and type in our function here, z equals f of xy. You can just put f of xy if you want. Is x squared minus 3xy plus y cubed. Let's go ahead and enter the point we care about. Negative 1, 1, comma f of negative 1, 1. And it's up there, so we can zoom out to see it a little better. There it is. You can see it's sitting on the surface like that. And now we'll enter our tangent plane. Z equals, and I forget what we had already, minus 5x plus 6y minus 6. There it is. Okay, now, this really and truly is the tangent plane. Okay, what did I screw up? Should look like the surface near the point. So if I zoom in, let me look this way. If I zoom in near the point, oh, not too far. There we go. The surface should look indistinguishable from the point. So I'm just going to double check. Did I type everything in right? X squared minus 3xy plus y cubed negative 1, 1 minus 5x plus 6y minus 6. Maybe if I did this, I'm going to make it a different. It's a little opaque. Do that maybe. Let's take a look here. We want to look near negative 1, 1. All axes, negative 5 to 5. So let's look. Let's do x between negative 2 and 0. Let's do y between 0 and 2. And let's do z between 4 and 6. Maybe this will help us see what's going on here. All right, yeah, that looks good. So if you look, we're looking near the point in space. That's the tangent plane that we got. That's the surface itself. Do you see the local linearity here? If I take this off, you see how that looks locally flat? And then if I take that off, how that looks the same? Is it coming through okay or not? This is a browser type thing, so I think it does have a desktop app as well. But that's the idea. That's the local linearity we want. Okay. That's why some people think the world is flat, because locally it looks flat. That just means that the surface of the planet is more or less differentiable. Okay. So there it is. I'll leave number 2 and 3 for you to do. So once again, I highly recommend when you write this out, you got your f of x, y, calculate your fx, your fy, and then calculate these numbers separately. Don't try to do everything at once. If you try to do everything at once, there's a good chance you'll make an error. Get all these numbers, plug them in, and then, GeoGebra or Desmos, either one, graph the function near the tangent plane. Okay, so really these are just nice little reviews. Let's actually graph the answer on this one, because as I recall, this was one of these functions we found the domain for back in the day. I had you graph it. Let's see how Desmos handles it. We're at the point 0, -1, f of 0, -1, which is, and then we've got z equals x minus 2y minus 2. Go. So we'll go over here, click on this. We want the x, let's say between -1 and 1. Do the y, say between -2 and 0. And the z, between -1 and 1. There we are. So take that off there. Maybe zoom in a little bit more. Wow, that was weird. Well, there we go. There's that surface sitting there. There's that parabolic domain we talked about last week. There's the tangent plane. We zoom in a little bit closer here. To x negative 0.5 to 0.5. And we'll do the y, -1.5, -0.5. That looks pretty good. You can kind of see that local linearity happening there. There's the plane. There's the surface without the plane. I was hoping that we could get it to zoom in. Oh, yeah, there we go. Oh, yeah, there we go. It's zooming in on the center now. So you can see as we zoom in, look what's happening to the curve and the plane. See how they're getting closer up here? There. Oh, that's beautiful. That's beautiful. Look at that. Okay, that's local linearity. Okay, that's what we want. All right, let's take a look at example 2. Because in order for us to make a tangent line, all we need to make a tangent line, well, let's go back. All we needed in Calc 1 to make a tangent line was we just needed the derivative to exist. If that derivative existed, we were locally linear, boom. In this formulation, in either one we take, in each formulation here, in order to get the tangent plane, we just need fx and fy to exist. So let's take a look at this function. This is a classic type of example. Look at the limit as xy approaches 0, 0 along these two different paths. Does the limit exist? So there's some of these on your take-home in your test, which is due on Wednesday. So this is good review. If I take the limit, let's go along x equals y. So everywhere I see an x, I'll plug in a y. So we're going to go along x equals y. So I'm going to sub in y for x. So y goes to 0 means x goes to 0 and vice versa. So I'll just replace this with the limit on y. And if I'm going into 0, 0, I'm getting close to the origin. I'm not actually at the origin. So what formula do I use? And so we'll plug x equals y in there. I'd have a y cubed divided by a y squared plus y to the fourth. Direct substitution gives me a 0, 0. What can I factor out of the denominator there? Yeah, you can do a y squared. 1 plus y squared. These things cancel out. I get y, I get 0 over 1, which is 0. So along that path, I get 0. Okay. Now let's look along the path x equals y squared. So let's go back and redo this. The setup is going to be the same. But now we're looking along x equals y squared. And once again, since we're getting close to the origin but not actually at the origin, we're going to be using this formula. I plug in x equals y squared, I get y squared times y squared, which is y to the fourth. And then the denominator, I get y squared squared, which is another y to the fourth, plus a y to the fourth. And so here I get y to the fourth over 2 y's to the fourth. So I don't have to do anything fancy here, because what happens to these y to the fourths? I cancel. I just get a half. So does the limit as you come into the origin exist? Along one path we get 0, along the other path we get a half. So that means the limit what? Does not exist. Yep. So this means that the limit doesn't exist. That means that the function's got some sort of fundamental thing going on there that screws it up. It's not continuous. And yet, let's look at the partials, fx and fy. So we'll do the fx. I'll leave the fy to you. If I wanted to figure out the partial derivative of fx at 0, 0, I'd go back to the definition I used last week. Right? That would be the limit as h goes to 0 of f of 0 plus h comma 0 minus f of 0, 0 all over h. So once again, I'm taking the derivative with respect to x at 0. So I'm going to change the x, keep the y the same. Be f of h0 minus f of 0, 0 over h. And let's see what would happen. For the first term, h is only approaching 0. It's not actually 0. So I'd be using this. So if I plug in f of h comma 0 to this, what am I going to get? Well, I'd have h times 0 squared over h squared plus 0 to the fourth. And so that numerator there would be what? 0, but the denominator would be h squared. And since h is approaching 0 but not actually equal to 0, I could go ahead and simplify that to 0. So this is going to be 0. The function is defined to be 0 at 0. And so this would be the limit as h goes to 0 of 0 over h. And once again, since h is approaching 0, it's never actually equal to 0, I can simplify the inside here to be 0. And so we literally did all that work for nothing, aka for 0. Any questions on how we're getting that to be 0? Likewise, you can go in and do the same thing for fy. The exact same thing is going to happen. Okay? So if I'm going to use our tangent plane, z equals f of 0, 0 plus fx at 0, 0 times x minus 0 plus fy at 0, 0 times y minus 0. Well, all this stuff cancels out, and I'm just looking at the xy plane. Everything's a bunch of zeros. So something's up. So let's see if we can get Desmos to show us what's going on here, and then that'll be it for today, and we'll have to come back to this notion of what we want to have happen a little bit more tomorrow. Let's go ahead and graph this function. And we'll graph the tangent, we'll graph z equals 0, and we want to look near the point 0, 0, 0. So for x, we'll do like negative 1 to 1. For y, negative 1 to 1. For z, negative 1 to 1. And you can see it's trying its hardest to explain what's happening here, but it is just all kinds of goofy, right? We could even do that lift. We could even look at, for example, we were coming in on x equals y squared. So we could put that lift in there. T squared t, and then t cubed over t to the 4th plus t squared. Or say, I'm sorry, t to the 4th. Oh, it was 1/2, right? It's coming in at 1/2 the whole time. T goes from, I don't know, negative 2 to 2. Okay. So we can even see like the zaniness of this, right? Coming in on this parabola, we're coming into a half. The tangent plane's down here. There's no way in the world you would describe this as being locally linear. The tangent plane does an absolutely terrible job, except on the principal axes. Except in the x and y directions, it looks like it's coming into 0. You follow? So the moral of this story is, just because the partial derivatives exist, and just because you can write an equation for a tangent plane, doesn't necessarily mean the tangent plane's doing what you want. Because what do you want the tangent plane to do? You want the tangent plane to approximate the surface, right? You want local linearity, and that's something we're going to have to talk about tomorrow. How do we get local linearity into Calc 3? It's more than just having certain derivatives exist, okay? All right, so enjoy the rest of your day. Play around with Desmos 3D, and we'll see you back tomorrow.